So up until Newton, and of course it was Newton who figured this out, up until Newton came along, scientists didn't actually know why planets orbited the sun or why orbital motion was a thing at all. So Newton was the one who figured it out, and it was a very simple thing. It was the force of gravity that was providing the centripetal force on the orbiting mass. So for example, we have the moon orbiting the Earth. We're going to use that as our example. So let me put my Earth here. Here's my moon. Now, there is a force of gravity between the moon and the Earth. The Earth is going to exert a force of gravity on the moon is going to exert a force of gravity on the Earth. But the moon being much smaller, we're going to notice the effect of the force of gravity on it. So the moon is always being pulled towards Earth. What we'd say is that the moon is always free falling towards the Earth. Now you might ask, well hang on, if it's free falling towards Earth, how come we're not looking up in the sky and the moon's coming crashing into us? Well, at the same time that the moon is being, pulled towards Earth, it's also trying to move away tangentially from the Earth. So the moon is also trying to move away with this tangential velocity. So with this moon trying to move away tangentially all the time, and then of course we have this force of gravity continuously pulling it down, what's going to happen is we're going to have a bit of a curve. And this is happening everywhere along the moon's orbit. So everywhere we're going, we're going to have that tangential velocity combined with that force of gravity towards the Earth. And what's going to happen is we're going to have that curved path, and this is actually going to cause the moon to stay in orbital motion. So at the same time that the moon is falling towards the Earth or free falling, it's also trying to move away from the Earth on that tangential path. So that combination of free falling towards Earth and that tangential velocity creates that circular orbit that we know about. And this is a point I want to bring up. When we have an object that's orbiting, it's in continuous free fall. Now the problem is, for us, that kind of conflicts with our brain, because we think on Earth, if something's in free fall, it's falling towards the ground and we can see that it's not doing the circular orbit. In space though, we have to account for the fact of that tangential velocity. Like that planet is trying to or the object orbiting is also trying to move away. So that combined with the continuous free fall gives it that orbital motion. But that's the thing, even like people in space, like when you look in the International Space Station, you see like astronauts, it looks like they're floating, and you want to say like, oh, there's no gravity there. That's not true. Those astronauts are in continuous free fall. It's just at the same time they're free falling towards the Earth, they're also having that tangential velocity. So it really plays with the mind, because it kind of goes against your perceptions of reality, but that is just something to note. So we want to look at the math behind Newton's observations. So he said that the centripetal force was provided by the force due to gravity. Now because we're not on the surface of the Earth, we're using the moon and the Earth, we have to use Newton's law of gravitation for this. So we're going to use little m for the orbiting object, and we're going to use big M for the object that's being orbited. So we're going to have something like this. So little m is doing the orbiting, big M is the one that is kind of staying in place. So centripetal force, we have mv squared over r. Now we're using m here, little m, because it's the small mass that's actually doing the motion. It's the thing that's actually experiencing the centripetal force. So we want to put the little m there. And then we have g, the little mass, times the big mass, divided by r squared. Alright, this looks okay. What I want to do though is I actually just realized this. I actually want to write centripetal force in terms of period instead. So I actually want to write this as 4 pi squared rm over t squared. So this is kind of actually what I should have started with here. But same thing. These are the same thing. Well, let's see if I can clean this up a little bit. I had the little mass, the one that's actually orbiting, its mass cancels out. Okay, that's convenient. I also want to divide, I'm going to bring the r's to the same side. So I have an r up here, but I have an r squared down there. Now they don't cancel. You can only cancel on both sides of the equation if they're in the same position. Like they'd have to be both in the numerator, both in the denominator. Since I have this in the numerator and that in the denominator, we can't cancel them. So I'm going to divide both sides, or I'm going to multiply both sides by 1 over r. So that 1 over r is going to take care of that r. And then r squared times r, we're going to get r cubed. So I'm going to have 4 pi squared over t squared. This is equal to gm over r cubed. So the last thing I'd like to do is I'm going to move this t squared to the other side. So I'm going to multiply both sides by t squared. And at the same time, I'm kind of combining steps. I'm also going to divide both sides by gm. Because I want this gm to be canceled here. And then I want this t squared to be canceled. So I have a lot of a mess here. But I have this 4 pi squared over gm on the left. And I have this t squared over r cubed. Now, looking at this, that t squared over r cubed, that should look familiar. This is Kepler's constant. We got this from Kepler's third law. So what Newton had done by his theories showing that the gravitational force was providing the centripetal force on objects in circular motion or orbital motion, it was consistent with Kepler's laws. Specifically, it validated Kepler's third law mathematically. So he found for objects orbiting, another way to find Kepler's constant is this 4 pi squared over gm. So just kind of interesting that Newton was able to essentially validate the work of Kepler well after the fact.